Greetings and salutations, alodats, defs, and here we're going into part 4 of polynomial functions. We're going to talk about the remainder and factor theorems. These are amazing theorems. I love their simplicity, and I love what they can tell us about polynomial functions. So the remainder theorem is one that states that when the polynomial p of x is divided by x minus a, the remainder is p of a. So let's check it out. We have this first example to just kind of evidence this, to say, hey, we have an example that shows that it works. It will be worth asking, why does it work though? And then of course, the key from a knowledge standpoint is just that you are able to use this remainder theorem to determine the remainder when division is performed. So let's kick this off. We've got this polynomial. We're going to use division to determine the remainder when p of x, that polynomial, is divided by x minus 2. My preferred method for the amount of space we have here is going to be synthetic division. So I'll set up my coefficients. We've got 2, -3, -4, and 5. And we're dividing by x minus 2. So as this goes along, we bring this 2 down there, multiplying for that, subtracting gives us this, multiplying gives us this, subtracting gives us that, multiplying again gives us this, and then subtracting leaves us there. And we recall that this last term is the remainder, as I'll see in orange. And then we have how many ones we have, how many x's, how many x squareds. But we're not really concerned about all that stuff. All this question is asking us for is the remainder. And we can say from this that the remainder is 1. And now we're going to determine the value of p of 2. So if we replace this x over here with a 2, what happens? Well, p of 2 is equal to replacing all the x's with 2's. We get some values out of here. 2 times 2 cubed is 2 times 8. 3 times 2 squared is 3 times 4. 4 times 2 is 8. 5 is 5. And collecting all of that, 16 minus 12 is 4. Minus 8 from that, we're at -4 plus 5 is 1. And we're amazed because they're the same. So it's an example that shows us that at least in this case, the remainder theorem would work. Now, it's not mandatory for you to know why it works or to be able to prove that it works, but in my opinion, it is useful to know. Again, you should never really accept anything as blind fact, just assuming that it works because you've seen one example that it does. Make sure that it's verifiable, that it's provable, that there's a solid rationale dictating why you believe what you believe. We've seen earlier that when you divide a polynomial by x minus a, that we can represent it as the quotient part plus the remainder over x minus a. That was that whole kind of mixed fraction sense of viewing it. If we take this, I'm going to do some spacing out here. And I multiply everything by x minus a. What I get is that a polynomial can also be written as the quotient multiplied by the divisor plus the remainder. Right? These x minus a's cancel out. These x minus a's cancel out. And that's what we're left with. When we have something like this, if we let x equal a, as we did below, well, then that's equal to q of a times x minus a. Times a minus a. My bad. Plus r. So I've just replaced all the x's with a's. Well, in that case, a minus a is equal to 0. Sure, I'll write that anyways. So we have q of a times 0 plus r. Anything times 0 is just 0. So p of a is r. And that, of course, right there is that statement of the remainder theorem that if you're dividing a polynomial by x minus a, the remainder is p of a. Again, not necessary for you to know or memorize, but I place high value in the verifiability of mathematics. So that's that. We'll use this remainder theorem now to just determine the remainder when these divisions are performed. I double dare you to give it a try right now. Go for it. And I'll show you what I got. Now in doing this, I'm just going to use a quick let statement so that if we can't just say p of negative 2 equals something. There's no p defined here. We should say let p of x be the dividend. 2x to the 4 minus 6x squared plus x minus 1. If we do that, then we can talk about the polynomial and what we're subbing into it. Now, the remainder theorem applies when we have x minus a. What would a have to be in this case that we're dividing by x plus 2? We'd be dividing by, a would be negative 2. So that's worth noting. And if a is negative 2 and we're taking p of negative 2, we can plug that in and see what we get. There's that. And then I can evaluate this. If you feel comfortable evaluating it all in one line, go for it. I'm going to take this in multiple steps. We are, of course, doing this without a calculator. That. 8, 6, 5. So in this case, we can say that the remainder is 5. And then this other one on the right, don't forget that let statement. Okay, so then p of negative 3, because if this is x minus a, we have to be subtracting negative 3. And that's equal to negative 3 cubed minus 8 times negative 3 squared minus 16, which is going to be a doozy of a number. Negative 81. What's 8 times 9 these days? 72 minus 16. 81, 72, 153, 169. Wow! What a behemoth. So there's our remainder when each of those is, divided. So that's the remainder theorem in use. And the remainder theorem is useful, but it leads us to a theorem we're going to use a bit more, and that's the factor theorem. But as a preamble for the factor theorem, questions. What's the remainder when 15 is divided by any of these. You can think about it in your head brains if you wish. When 15 is divided by 3, the remainder is 0, because 15 divided by 3 is exactly 5, remainder is 0. When 15 is divided by 4, well, 15 is not a multiple of 4, so we're going to get a remainder. 4 goes to 12, so 15 divided by 4 gives you a remainder of 3. 15 divided by 5 has no remainder. That's exactly 3 with remainder 0. And then 15 divided by 6, ooh, not a multiple, so that's also a 3. And we could do this with other numbers if we wanted, right? What happens if we're talking about 7? 15 divided by 7 has remainder 1. So we can figure this remainder till the cows come home. I've never used that phrase before, I think, except in high school drama, maybe, where I had to play. Anyways, of the values 3, 4, 5, 6, and hey, even 7, why not? Which ones are factors of 15? And we can figure out factors of 15 if we need to. We have that ability. But it's just 3 and 5. We know that they are factors of 15 because they divide evenly into 15. We know that they divide evenly into 15 because they have no remainder when that division is performed. We can see that for each of those, the remainder is 0. So, if p of x is divided by x minus a, and that quotient, or the remainder, is 0, then x minus a must be a factor of, side of the whole thing, of the polynomial itself. And there it is restated. So we can use the remainder theorem to determine what the remainder is. And then once we have that, we can decide whether that divisor is a factor or if it's not. So 2 steps in this each time, where the first one is to find the remainder. And the second step is to justify a conclusion, or justify a stance. So for me, first one I'm going to find the remainder. So I will let p of x be equal to this polynomial, oopsie daisy, that we're playing with. I want to divide by x minus 2, which means that a is equal to 2. P of 2 is 2 squared plus 2 minus 6, which is equal to 0. So I've got that info, and from that info, I can justify a stance. The remainder is 0. Therefore, x minus 2 is a factor. Neat. I double dare you to try the remaining 2 examples. So pause the video and then fast forward if you need to, and see if you get the same things I get. Same steps. 1, I will find the remainder. And then I will justify a stance. Not a lot of room here, Thide. I know. I'm sorry. That. 16 and 6 is negative 10. 28 and negative 18 is positive 10, so this adds up to 0. Honestly, I could... Don't mind me. I'm just copying and pasting. And last one. You're right. I could just do that again. Yeah. I don't know what that is. 64. 8 times 9 is something. Great. Where are we at? Negative 8, negative 4, negative 3. That remainder is negative 3. That remainder is not 0. As such, we arrive at the following conclusion. I'm copying from above. Classic me. So that's those ones done. That's the remainder theorem and factor theorem. Two beautiful theorems that are going to help us learn how to, or they'll help us when we're trying to figure out how to divide large order polynomials, something that are more than degree 2. When we're trying to identify what we can even divide by. This is what's going to help us essentially get the prime factorization of polynomials. Useful stuff, beautiful stuff. And if you know how to do the remainder theorem, how to prove it, that is a beautiful thing, and you're a beautiful person. Not to say that you're not a beautiful person if you can't. You can be beautiful in a whole bunch of ways, but math is beautiful. So, anyways, there's some stuff to practice with. It's quite a bit. Hopefully a lot of it goes by quickly because some of these examples some of these types of questions are very quick ones. Just make sure you don't get any communication errors by things like forgetting this let statement. Let p of x be something. But give that a try, give it a go, give it a whirl. Give it a shot, give it a stab, give it a spin, give it a try. And if you run into any difficulty at all, please do let me know as soon as that happens. And of course, you can always let me know if you have questions on this lesson as well. Reach out to me via Teams, or you can see me in person in school. That's all I've got for now. I will see you in the future. Goodbye.